Welcome to the Mentored Engineer. In this video we are finishing up our series on maintaining level by talking about hydraulic leveling. Now this is the trickiest one of them all, and there's a bunch of things that need to be factored in. So a traditional setup, if you were looking at some sort of man lift, would look just like this. You have a beam, you have a cylinder at the boom tip that holds a platform level. You have a cylinder that will articulate the boom. And then you have a cylinder here that will tell this cylinder what position it's in. Okay, so a couple things you need to know is you want similar geometry on both of these cylinders. Okay, so the bore size and the rod size and the stroke should be equal. There should not be a reason to differentiate the two. You're not going to get good results if you do. All right, next thing is you're going to want to have extra stroke on this cylinder. You don't want to get into a situation where this cylinder is not quite all the way extended, but this cylinder is extended already. When this cylinder, which is much more powerful than this one, extends a little bit more, it is going to pull this cylinder apart and bad things are going to happen. So don't do that. Make sure you've got extra stroke in this one. Okay, so you also want to focus on load holding. Since this isn't a mechanical system that's tied together, you're going to want to prevent against hose rupture, so you're going to need some load holding valves on this cylinder. Alright, you're also going to want to take into account deflection. Alright, we'll talk about that in just a minute. So to keep these cylinders timed, you're going to want to do a couple things with your hydraulics lines. You're going to want to look at the velocity of oil that's exiting this cylinder and coming into this cylinder, and you're going to want to keep that to a speed of less than 10 feet per second, same as you would have for a return line. And the reason for that is you don't want to have large amounts of pressure being used just to move the fluid back and forth. You want the fluid to do the work of maintaining level and not possibly getting out of a counterbalance somehow just because it can't move fast enough. All right, so that's a call for increasing your sizes. You also want to keep your pressures below 2,000 psi. This is assuming that you have a 3,000 psi system. So you want to keep those well below your working pressure so that you're not trying to force oil again some ways, or somehow where it doesn't want to go too speedily. All right, and that goes along with the speed requirement of 10 feet per second. All right, so the last thing here is you also want to consider deflection. So if I look at this beam as a stick, I've got a force here, and it's kind of gonna droop down. All right, I drew it well more, but you know, let's say this is 5 degrees. All right. That's a bunch of deflection. So if I design this perfectly, this thing's going to tilt down here at this point, but I don't want it to do that. I want to account for it. But then when it's all the way up, you know, my deflection, you know, could be, I don't know, half a degree. All right, so we don't want to have a situation where that is like that. And I'm actually going to be making a calculator for this that will include deflection as you go up. So you can use that to anticipate and design for your geometry. Okay, so if we're not designing for deflection, we can basically set this up very simply. We're going to have our boom here, and it's going to keep going back. And then we're going to have the leveling system here. And we're going to have our cylinder. And if we draw our coordinates, such as this, put X and Y, oops, Y, not X, not another X. All right, we're going to have a distance here. We'll just call it A. All right, you can have a distance here, call it B. If we look at this piece, we'll consider its own piece, but we'll have its own X and Y. All right, we're going to have perpendicular distance C, and then if we have a distance here, it'll be distance D. All right, if you're not considering deflection, just maintain these ones over. And your section may be so small or short that you know, it doesn't deflect. So you can just copy this geometry on each end. Now the rotation can change. You know, we can draw our coordinate systems any way we like, but as far as these two components, they're going to have to be machined in the same way. Okay, so the last thing we're going to want to consider here is our load holding. All right, and I mentioned before that you want to have load holding on this cylinder, and I mean directly on this cylinder, coming from the manufacturer with it on there, no hoses in between. All right, so in this cylinder I have two counterbalance valves. I would select something in the neighborhood of a 3-to-1 or 4.5-to-1 counterbalance for valve ratio, and I would definitely have it set at least 10, if not 15% higher than your system pressure. Okay, so I have cross-piloted or cross-ported pilots on this valve. So if in this case it's trying to work this way, the cylinder's in compression, I'm trying to force oil out of here. What happens is it comes out of the cylinder, can't go through there, comes over to this check valve, can't go through that check valve. So what it either has to do is it has to build up enough pressure there where it will overcome the spring right here, which basically means it's building up 3250, 3500 psi to open this up. So that doesn't normally happen, but then the fluid would come back down here and it'd go into the base of this cylinder. All right, so if this hose breaks, all right, I got to make 3250 up here to get that to come down, which is a good thing. All right. However, if I pressurize the other side of the cylinder, this line right here actually pops it up open at the ratio that we have indicated. In this case, if we use a 3-to-1, if I had no load on the cylinder at 1000 psi, this would open up and oil would flow back. However, most of the time I'm going to have at least some load on there, maybe only 100 to maybe even 1000 psi, could be up to 2000 psi based on my recommendation. But that all helps us and reduces the pressure it needs to open up this valve. All right, and I have the same system on this side. So when I pressurize this line, it will open up this valve and allow oil to come out the rod side as I put oil into the base side. Okay, so that's how that works. Okay, so in a practical example, we're just going to ignore this stuff over here right now. So this is for retiming. All right, if I'm articulating this up, this cylinder is going to extend. We want this one to retract. Okay, so what's happening is I'm going to pull this cylinder, which is this cylinder, and pull it out. And oil's going to come into this line and need to come back into here. All right, so I'm going to pull oil and I'm going to compress it and push it out so it's going to build pressure. It can freely go past this check valve into the rod in the cylinder and start retracting it. All right, on the other side, it's got to build up pressure first. So it's got to come out here, it hits that check, hits this block, and then it's got to wait until the combination of the pressure in the cylinder and the pressure from the cross pilot is enough to open it. And at that point, it will come back and return to the base of the cylinder. Very simple. So the opposite works when you start retracting. You're going to compress this cylinder, and then you're going to compress that one as well. All right, so that's basically how that works. If you have equal volumes here and here, as far as rod and bore sizes, it should work out pretty well. All right, now this over here is just another counterbalance valve, and it's attached to a directional control valve. And all this does is it allows for two things. If you, when you're first priming the system up, you need a way to get oil in there. All right, so you would use this. You stroke each cylinder. You'd probably, you'd want to go all the way up with it and all the way down, and making sure that you're articulating the bucket fully up and fully down, just to get full oil in those cylinders. You might want to do that 2 or 3 times to get all the oil you need into the system. Okay, so what also happens is this prevents against thermal expansion or just too much oil in the system. So as you build up pressure, this thing is going to lock it down, except when you're using this valve or when you have just too much pressure in the system, and that oil will go back. Now, I said here you're going to want a 3-to-1 or 4.5-to-1 counterbalance valve ratio. Here you're going to want 10-to-1. This is purely load holding. This is no smoothing out kinks in the system. This is just load holding. Theoretically, you could run these 2 lines right back to the directional control valve, but over time, your directional control valve is going to leak oil. And in this case, if you're dealing with, say, a 2.5 or 3-inch cylinder, a couple drops in it, that can make a big difference. If you're sitting up at the top holding, and then all of a sudden you come back and you're going to get out of level pretty quick. So we put a counterbalance valve in there just to hold that tight, and there's no leakage through a counterbalance valve because they are designed to not leak. All right, well, thank you for watching this episode of The Mentored Engineer. We hope it was helpful to you and that you learned something. Thank you. Bye-bye.